So in this lecture, I'll cover matrix stiffness method in order to get PCR. I don't know whether you already have learned matrix analysis method in undergraduate study. If you have learned already, then my lecture can be easily understand. Otherwise, you feel a little difficult. As you see here, this is displacement and member force corresponding to slope deflection method. So this is some member force and displacements corresponding to matrix analysis procedure. So from this slope deflection method, we will derive that stiffness matrix corresponding to this kind of matrix stiffness analysis coordinate like that, 6 by 6. So finally, we will get the second order stiffness matrix, K equal K0 plus Kz. K0 means linear stiffness matrix. Kz means the stiffness matrix corresponding geometric nonlinearity. Another term is first order linear stiffness matrix. Kz is a geometric stiffness matrix. And then we will take the determinant of this stiffness matrix equal to 0 for bifurcation analysis. For this bifurcation analysis, we can get PCR from determinant K, right? Finally, we get the 1.83 EI over L square versus 1.82 EI over L square that we already get. So it is very close. A little difference, it is come from Randolph error. Okay, it is the whole procedure. So I'd like to explain step by step from now. I'll use the textbook. Again, this is the coordinate R2, R1, R2, R3. This is end moment. D1, D2, D3, blah, blah, it is end displacement corresponding to matrix analysis procedure. This is slope deflection equation, member force and then displacement. As you see, member force MA, MB, here is P and P compression, and then we have a shortening E, and then angle theta A and theta B. And then again, we also get that the shear force V equal MA plus MB over L, right? If you take the equilibrium, if you take the moment here, the summation of moment equal to 0, right? Then you can get this shear force, right? Let's look at this one. If you compare these two, we can get equilibrium relationship. Let's see, this R1, R1 is axial force. Here, R1 equal P. In the same way, you can get R1, R2, R3, R4, R5, R6. That is equilibrium relationship between two different coordinate systems. Let's look at the kinematic. Kinematic means the displacement relationship. So this E is shortening. The shortening is minus D4 minus D1. D4 minus D1 is the elongation. So here minus is shortening. That relationship. Theta A is this one. Then as you see here, D3, that is rotation. And then you have another element, that is D2 and D5. That is vertical displacement. You can get the difference between this vertical displacement, let's say delta, divided by this L. Then you can get the theta, right? Another theta term. Yeah, that one. So theta A equal D3 plus that is the difference in vertical displacement and L, right? And then theta B, you can write like that. In the same way, you can write this equilibrium relationship in this matrix form. R1, R2, that is member end forces in matrix analysis. That is the end forces in slope deflection procedure. That is some transformation matrix. R1 equal P. R2 equal minus 1 over L. MA plus MB, as you see here. And then again, you have some kinematic relationship. This one in matrix form like that. You can write E theta A theta B. E equal D1 minus D4. Okay, like that. That way. And then you know the relationship P equal axial force equal EA over L E. So what is E over L? That is epsilon. Why? Strain. So E epsilon means stress. Stress times area is P. That is the relationship. MA and B, your well-known relationship. Okay, slope deflection equation. This equation can be written in this matrix form. P, MA, and B, L, EI, like that. E, theta, A, theta, B. You see this equation, E, theta, A, theta, B. This equation. So you can input this equation into here. You see this equation, P, MA, and B can be input here. Again, if you see this equation, if you input this equation there, and again this equation, input this equation, then you see if you input here this equation and this equation, then you can get this kind of 6 by 6 stiffness matrix. This is and forces and displacement in matrix analysis procedure, like that. 6 by 6 matrix. So we can rewrite this equation as this symbolically. This is bold character RNS. That is RNS. And this one stiffness KNS. This one is D. NS means non-side sway. Up to now, we did not consider side sway, non-side sway. So symbolically, we can write this form instead of this matrix form. Then, if member is permitted to sway, then we have this kind of delta. Delta equal D2 minus D5. This kind of delta. This delta related the shear force. This delta caused the shear force. So let's say this R2 is shear force. This shear force equal minus PL D2 plus PL D5. That is shear force due to this member sway. This equation can be written in this symbolical form. This RS is member forces regarding the sway. In case of sway, KS is stiffness matrix for sway. T is displacement. The element force and displacement relationship can be written in this form. We can divide into two. One is RNS and RS. So what is RNS? Force in case of non-sway. That is element force in case of sway. And then stiffness matrix also. RNS equal KNSD. RS equal KSD. Through this relationship, K equal RNS. Stiffness in case of non-sway. KS stiffness in sway case. We can write this. So ultimately we can get the K stiffness, element stiffness like this form using KNS plus KS. This is KS, okay? This is KNS. Add together, okay? Then this term P here. So here, this K include P. If you add together and rearrange the equation, then you can get the P term. What is K? K equals square root 2 P over EI. If you calculate this one, then you can see minus P over L. You can get that value. So this one is the stiffness matrix of an element. As you see, this II, this Ij is function of sine, cosine, something. Somewhat complicate the equation. Do you remember? If it's the previous notebook, then you can see, you can recall the equation of Sii, Sij. If you use the original equation, sine, cosine, something, then it becomes very complicated equation. In order to show this equation simply, then we introduce pi 1, pi 2 values. Okay. Then what is pi 1, pi 2? That is this one, pi 1, pi 2. These equations. As you see here, sine, cosine, sine. It includes like that. Here you have a pi 3, pi 4, so pi 3. And As you see, this is some sway case, member sway case, the figure for getting stiffness matrix for sway case. If you have the delta here, you can have some shear force like that. From this figure, you can get this equation because this is D2 direction in matrix analysis procedure. Okay, by the way, you expressed the stiffness matrix by this pi 1 up to pi 4. And then, you know, we have some power series expansion like that. So sine KL equal KL minus KL over cube 6 blah 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 cosine KL tension something like that. This is compression, this is tension. So if you use this power series expansion, that is a sine cosine here. If you use power series expansion, that is pi 1, pi 2, pi 3, pi 4. So as you see, it looks very complicated. So in order to make simplicity, we just take first two terms. As you see, this term is infinite term. So we take just two terms, first term and second term, from this power series expansion. This expansion must be applied this equation, and then you take just the first two terms. You have this one and this one, first term, second term. This first term is called linear stiffness matrix. If you ignore geometry nonlinearity, then you can just use this matrix. If you consider geometry nonlinearity, that means if you want to do second order analysis, you have to consider this term. That is a geometric matrix. So that is K0, Kz. At the beginning of today's lecture, I already mentioned K0 and Kg. I already mentioned I will drive these two stiffness matrix. We got it finally. So K equal K0 linear stiffness matrix. Kg is nonlinear stiffness matrix or geometric stiffness matrix. So that is element stiffness matrix when we are doing matrix analysis approach. Now what we are doing? We are doing to get PCR. So in order to get the PCR, I show you some this first order elastic stiffness matrix and second order geometric stiffness matrix. That is element stiffness matrix. Let's look at this one. That is, as you see, we have the portal frame. The original one is this portal frame. Do you remember? We already solved this portal frame using slope deflection equation in the previous lecture. We use the same thing, but the symmetric condition, left hand side and right hand side, symmetric condition, we cut here in order to make problem simple. So we just consider this element 1 and element 2. Let's look at the local coordinate system. Element 1, if we ignore the axial force, for simplicity, we can write down like that. That is R2, R3, D2, something like that. This one is R2, R3, D2, like that. Then we can make 4 by 4 matrix like that. In this stiffness matrix, we ignore the shortening due to axial force. We consider axial force, but we ignore the shortening. For simplicity, we can ignore the shortening due to axial force to get the PCR. It does not influence on PCR. You use this equation, element stiffness matrix. You apply here. Apply element 1 and element 2. Then you can get element 1. Apply, let's say, element 2, the stiffness matrix. As you see, the axial force apply here, not here. There is no axial force at the beam, so you don't have any geometric stiffness matrix term in beam. So K1 stiffness matrix, K2 stiffness matrix, and then you have to consider global coordinate. That means here, this one is global coordinate. R1, D1, R2, D2, R3, D3, R4, D4. That is global coordinate corresponding to total structure system. This one is, we call it the element coordinate or local coordinate. As you see, this is local coordinate, local coordinate. So we have to transform into global coordinate from this local coordinate. So as you see, there is some relationship. This D1 equal here D6, right? If you match together, D3 equal D2, right? You have that kind of some relationship. So if you compare those relationship, you can D2 equal D4, right? D3 equal D2 for element number 1, right? That relationship. That is local coordinate, this is global coordinate. Let's look at the element 2. Also, you have this relationship. You can write this one symbolically. This D1. You use the bold character. D1, that is T1. That is global coordinate D. Element coordinate D2, displacement D2. That is T2, that is D. So T1, T2 called transformation matrix. If you establish R1 global coordinate, R, small r, and local coordinate. If you see here, look at here. As you see, this R1, this forces, R1, R6. You can match like that. Here, R1, small r6, right? Match like that. So you can find this relationship. For element 2, you can find this relationship. As you see, this the transformation matrix here regarding the displacement. And then look at this one. By investigation, what do you find? This one and this one. This one is diagonal term. This one is diagonal term. But here 1 and moved back here, back here. So these two matrices transpose relationship. I want to see this one together. Yeah, we can write this R, global coordinate R, and then small r. There are transpose relationship. T1, transformation matrix transpose. Okay, R. Okay, R2. This some relationship. So R equal R1 plus R2. R1 equal this T1 transpose R1, T2 transpose small r2. The small R1 is K1 D1. Small R2 is K2 D2. If you input this equation into here, then you can write T1, TK1, D1, T2, TK2, D2. There is some relationship. D1 equal T1D, right? D2 equal T2D. If you input this relationship, then you can get this one. And you can rewrite like that. So as you see, this R is a global coordinate force, global coordinate displacement. That is what? Global coordinate stiffness matrix. So global coordinate stiffness matrix can be written the local coordinate stiffness matrix, member stiffness matrix before transformation, transpose, and transformation. So T1T, K1, T1 plus T2T transformation transpose, K2 transformation matrix. This is a way to get the stiffness matrix of the global coordinate. So we can rewrite like this, sigma. This matrix operation, then finally you can get this global coordinate stiffness matrix. If you use this lambda term like that, then this equation can be written like this. And then, as I mentioned before, take determinant of stiffness matrix. Then you can get PCR equals 30 lambda EI over L square. So this lambda, in order to solve this equation, is lambda equals 0.061. So 1.83 EI over L square. That is your PCR. Up to now, I show you how to get the PCR using matrix analysis. Let's look at the PP, plastic collapse load. In fact, in order to get this plastic collapse load, we learned plastic analysis and design courses. We spent 1 semester to get this PP. But here I would like to show the simple example. We use the mechanism method. PP applied here, we assume this plastic hinge forms like that. Plastic hinge form here and here. Then if this angle theta, then this angle is 2 theta. L over 2 theta, this displacement. So we get the internal work. MP times theta equal work, okay, energy. MP theta, here, MP times 2 theta. How about here? There is no plastic hinge, so no work occur. So that is plastic hinge here, plastic hinge. And theta times theta, then we get the internal work. External work is PP times this displacement. PP 1 over L theta, right? So internal work, external must be identical. From this equation, this collapse load, plastic collapse load is 6 MP over L. That is a procedure. How about this portal frame? For this example, 1.5 P, then this P. Firstly, we get the beam mechanism. We consider plastic hinge form here and here and here, and it will be collapse. It is called beam mechanism. So if you assume theta here, then this one theta, this one is 2 theta. The internal work is, that is MP, 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 theta, theta, 2 theta. So 4 MP theta times 1.5 this displacement. Then you can get P1, collapse load. Another mode is a sway mechanism. That is plastic hinge forms, and plastic hinge form, that it will be collapse. It is a sway mechanism, it is called. MP, MP, theta, theta, 2 MP theta. P2 L over 2 theta. So P2 equal 4 MP over L. How about combined mechanism? Combine these two, in fact. Then this one is 2 theta. If we add together, 2 theta, this 2 theta. So MP, MP, 2 theta, 2 theta, 4 MP theta. Internal moment, internal work. External work is 1.5, and this displacement, this one, P, this displacement, this one. So collapse load of this combined mechanism is P3. So plastic collapse load must be minimum of these three, 16 MP over 5L. So this combined mechanism is a real collapse mechanism. So you get the PP. Now you get the PCR using slope deflection or matrix analysis, right? And then you get the PP, this kind of the mechanism, okay, using mechanism approach. Now you know PCR and PP. Then you can approximately get PF, failure load, okay? At the beginning of this lecture, I already mentioned, okay? Merchant ranking suggests that equation. Do you understand? Then finally you can get PF. See you next time, everybody.